This video will be the first half of Chapter 10 of Walding with the in-text questions. Okay, question 1 reads, what has more thermal energy, a cup of water at 100 degrees Celsius or a bath full of water at 40 degrees Celsius, and or why? So the question is then, well, what does thermal energy require? Okay, so if we think about that, thermal energy, if we check our text, is dependent on the mass and the temperature. It is not just the temperature, so the initial assumption over here, thermal means hot, we're talking about heat, the cup is hotter, so it must be the cup. In which case, why didn't it just say what's hotter, a bucket of water or at 100 degrees, or a bucket of water at 40 degrees, which has more thermal energy, a bucket of water at 100 degrees or a bucket of water at 40 degrees. In that case, the 100 would be fine. But because we've got a cup versus a bath, we've got now another factor to consider. So if we list that off, cup, I don't know, mass might be about 200 grams, and the temperature is 100 degrees Celsius. But if we think about a bath, well, what's the mass within a bath? Go grab yourself a 2 litre jug of milk, or maybe a 1.25 litre bottle of soft drink, or a 2 litre bottle of soft drink, go pour it in the bath. How many of those could you fit in a bath? If we can fit 10, we're now up above 2 kilograms. Now, I'm pretty sure, if we put 10 of those bottles, we're above 20 kilograms. And I know that I can fit 20 kilograms of soft drink plus ice in my bathtub, so it's definitely at least 20 kilograms. So let's just go with 20 kilograms. If you're not certain, feel free to test that. So this 0.2 kilograms to 20 kilograms, this is 100 times bigger. Even though this number is bigger, but this is only 2.5 times bigger in that direction. Alright, so I mean, yeah, it's hotter temperature, but there's a lot more mass, there's a lot more particles in that bath, and thermal energy requires us to think about both the mass and the temperature. So in this case, bathtub wins. Okay, that one has more thermal. Okay, 2a. Question 2 reads, steam at 100 degrees Celsius will give you much more severe burns than water at 100 degrees Celsius. And which one of the molecules moving the faster? Now, speed of a particle only depends on temperature. Being as both things, steam and water, at 100 degrees, the answer is neither. Okay, same temp, and it's always good for these sort of things to give a reason why. Same temperature equals same speed. Okay. Now, like if this was a C sort of level question, the neither bit would be giving us the C. This bit here would be pushing up to a C+. Doesn't really, I mean, you have to think of it anyway. So do try to use answers like that. And which one do the molecules have greater potential energy? It's not asking about thermal energy. Okay? It's not talking about temperature, it's asking about potential energy. So potential energy is stored energy. It's energy that is not being actively used in a kinetic sort of sense, in this case how fast the particles are moving, but just stored in the state of the matter. And so in this one would have to be the steam. Now why? Well, if you have 100 degree water, you still need to add energy into it to make it turn into steam. That energy has to go somewhere. It is stored in the new change of state. So of the two, the molecules with greater potential energy is the steam. Finally, why are steam burns more severe? Because steam has more energy. It's basically the kind of question from B leads to the answer to be C. Okay. Steam has more energy. So if you stick your hand in some steam, it's going to thermally equalize with your body, and that's what a burn is. You're receiving energy from something, or so much energy from something, that it ends up damaging your cells. So it receives the energy of the phase change, and then the energy of the temperature on top of it. So you've got extra energy being given. Okay. Question 3a. What is the name given to the internal energy of a substance? Well, if you just scroll back up, it tells you that it's thermal energy. So thermal energy is about all the internal energies of a system. It is both the kinetic energy, how fast the particles are moving in terms of temperature, and the potential energy within, such as state. Okay, so that means, well, if we think about it, if I have to add energy to water, turn it into steam, even if they're both 100 degrees, then that potential energy must also be part of the thermal energy process. Okay. Question 4. Mr. Joule is doing 100 joules of work on several quantities of water. We've got 3 volumes there, 100 ml, 300 ml and 500 ml. Remember, 1 milliliter of water weighs 1 gram, so 100 ml of water is 100 grams. It doesn't work for other liquids, so don't make the mistake of doing that, but it does. It's a nice easy conversion for water. That's why the volume was chosen like that. Which sample would gain the most thermal energy? Why? Well, they're all going to say the same. Why? Because only 100 joules of work is being done. Okay. Thermal energy is energy, joules is work is energy. It's just work, it's energy that is currently doing something. And it doesn't matter which one we give it to, it's still just going to be 100 joules. So if I give $100 to the classroom, yep, you'll about 20 of you, a little bit under 20 of you, but let's say it's 20, in which case then you get $5 each. But the total amount of money given to the class is still the same. If I only gave $100 to the grade 12s, they'd each get $20 instead. So yes, same amount of energy, but now the money's being distributed differently, and that analogy is quite good to think about for question 2, which sample's temperature would increase the most. Remember, temperature and thermal energy are not the same. Thermal energy depends on temperature, but temperature is just talking about how fast the particles are going. It doesn't care how many particles there actually are. So we can think about it for richness. If I gave $100 to the whole class, yeah, the whole class is $100 richer. But you're only $5 richer each. If I gave $100 to the grade 12s, the class is still $100 richer. But because there's less of them, they're now $20 richer each. And so if we think about the masses there, 100 milliliters will be the least amount of mass. So each particle there will get the more of the share of energy. 100 mil, least amount of mass to share energy. I hope that makes sense there. Question 5. Okay, we've got some temperature conversions. Now, how to do this is right above it. I honestly don't think there should be any problems with these. I am just going to talk about 5e though. Okay, the first 4, if you can't do them, there is a big problem. But 5e, so negative 300 degrees Celsius, if we need to turn that into a Kelvin, we add the 273, so negative 300 degrees Celsius, add 273 to it would be negative 27 Kelvin. But what's wrong with this number? Okay, this is impossible. Okay, it is not a number that can work. Okay? You cannot get negative Kelvin temperatures at this point. If you define temperature as the rate of change of entropy, which is something we don't cover yet, you can get a negative temperature, but that is a situation where it is a very, very hot substance. So negative Kelvin temperatures do exist, but it is not something that is observed or calculated or even thought to worry about in this unit. So for now, impossible. If we go down to question 6, again, A, B and C, you shouldn't have any dramas, but if we look at D, minus 50 Kelvin, same thing, this is an impossible number to work with. Okay, again, no such thing as negative Kelvin. The rest of the questions, if you can't do that, there is a very, very concerning problem there. Okay, question 7. Now we're down to thinking about energy and temperature. So we're asked to calculate the heat energy absorbed when 1.5 kilograms of paraffin is raised from 15 degrees Celsius to 50 degrees Celsius. So let's list our variables. First off, first number I see is 1.5 kilograms of paraffin. M equals 1.5 kilograms. We're told that the initial temperature raised from, that from is giving you the context that that's the initial, and final equals 50 degrees Celsius. So therefore delta T must equal 35 degrees Celsius, final minus initial. Now we're told that it's paraffin, which tells us that there must be a specific heat capacity, and if we scroll up to page 245 where table 10.1 is, we see that it is 2200. Excuse me. 2200 joules per kilogram Kelvin. Do be careful with the kilogram bit. You want to make sure your mass matches up for it. And we're asked what is the energy needed, so Q equals, don't know. So Q equals MC delta T would equal 1.5 times 2200 times 35 equals 0.5 times 2200 times 35. 115,500 joules is about 1.16 times 10 to the 5 joules. Why did I choose 3 decimal places? All those are in all of those are 2 precision. So I'm just going to use 3 for the sake of it. We could do 1.2 as well, but going a little bit extra on a math question isn't a bad thing. Okay, how much heat could be absorbed by a 3 kilogram block of steel at negative 10 degrees, block of ice at negative 10 degrees before it reaches its melting point? So we need to think about similar sort of idea. We're asking about heat, so we want a Q. We've been given a mass, let's write that down. M equals 3 kilograms. We're told that it's a block of ice at this number, 10 degrees, so Ti equals negative 10 degrees Celsius before it reaches its melting point. Now, that's where a little bit of extra information is hidden. If I was to ask you what is the melting point of steel, or what is the melting point of aluminium, or what is the melting point of sodium, it's not something I'd expect you to know. It's not something I'd expect you to know for an exam. But if I ask you what is the melting point of ice, that is expected. Okay, it's not something that would be written down anywhere on your textbook or anywhere on your exam to refer to. The melting point of ice is something that should be known, and you should recognise that that's a number in the question there. So therefore our temperature final equals 0 degrees Celsius. So our delta T must be 10 degrees Celsius. And we're asked, we need the specific heat capacity of ice. So again, go back, it's not 4200, that's the specific heat capacity of water. Ice is 2100. Okay, and we're asked to find what is Q. So do the same thing as well. Q equals MC delta T equals 3 times 2100 times 10 would be 63,000 joules. Or 6.3 times 10 to the 4 joules. Okay. Question 9. A liquid is heated in a beaker. If it is found that it takes 7,500 joules of heat to increase the temperature of 500 grams of the liquid by 6 degrees Celsius, what could the liquid be? Okay, so similar idea. Let's list what we've got. We've got 7,500 joules of heat. That would be a Q value. We've got to increase the temperature by 6 degrees, and we've got 500 grams. So mass equals 0.5 kilograms. Always use SI units. And we're told that the delta T equals 6 degrees Celsius. We don't have a temperature initial and a temperature final, but that doesn't really matter in this case. We're asked to find out what it is. So we need some sort of numerical thing that could tell us what it is. In this case, we're talking about specific heat capacity. So remember that every type of matter has its own specific heat capacity. So if you know what the specific heat capacity of a sample is, you've got a pretty good idea what it's going to be. Do note though that like if it's a mixture of different things, the mixture itself will have its own average specific heat capacity based off of the masses and the percent volume, or the percent volume and the different specific heat capacities of the different things. It's kind of like a weighted average. So in this case, C equals, don't know, so let's write that up. So Q equals MC delta T, Q 7500 equals 0.5 times delta T is 6 times C, so C equals 7500 over 0.5 times 6, 100 divided by 0.5 times 6, it will be 2500 joules. Don't forget the unit, so joules per kilogram. We'll carry degree C or Kelvin. Remember, the change is the same. If instead you were not too careful with how you put that into your calculator, you went 7500 divided by 0.5 times 6, and you didn't put the 0.5 times 6 in brackets, you would end up with 90,000. That would be a calculator error. You would lose a little bit of marks for it, but do be careful with that sort of thing. So we've got a value. It's coming from the textbook. Let's check the textbook. And we see that 2500 correlates perfectly with methylated spirits. Therefore, methylated spirits. Alright, this video finishes off here. Question 10 through to 19 will be in the next video. Thanks guys, bye.